Okay, so in this video I'm going to have a look at the sine rule, and later on we'll have a look at what's called the ambiguous case for the sine rule. So I'm going to do a couple of examples where we use the sine rule to find the angles and sides of triangles that are missing. So just before we start that, let's have a look at the Cartesian plane here. We've got an x and y axis, and we know that if we have an angle here in the first quadrant, any angle here at theta we'll call it, that sine, cos and tan are all going to be positive in the first quadrant. So they're all positive here. Now if you move into the second quadrant, if you have any angle here in the second quadrant, so any angle from here to here, only the sine will be positive in the second quadrant. And it's this idea that in the second quadrant sine is positive that we're going to talk about later on when we talk about the ambiguous case. So the sine of an angle will be positive in the first and second quadrant. Now just to look at the other two, which we won't be using, but if you take an angle, say here in the third quadrant, so if we take, for example, this angle here, so we have to go all the way around to here, that particular angle, they're all positive here, sine is positive here, tan is positive down here, so sine and cos will be negative. And finally, if we have an angle down here, if you have an angle all the way down here, so all the way around to here, that particular angle, then we would just be looking at cos being positive down here. So sine and tan will be negative in this quadrant. But what we're going to do is concentrate on the first two quadrants here when we talk about the sine rule. Okay, so that's just a little bit of revision. Let's have a look at an example of how we use the sine rule. Okay, so let's take a triangle. I'm going to take this triangle here. Let's draw it out. And we're going to call this triangle A, B, and C. Actually, you know what? I think I'll put the B over here. I'll put the C here. Okay, and we're going to say this is 60 degrees here. And this is 15, let's say, centimeters, and this is 13 centimeters here. Okay, so here we've got a triangle ABC. We have one angle and we have two sides. Now the two sides are not enclosing the angle. In other words, the angle 60 degrees is not here. So I'm going to use the sine rule. If in fact we had two sides and the angle enclosed, we can use the cosine rule, which is a different video which you can have a look at. But in this case, we're going to use the sine rule. So the first thing I'm going to do is I'm going to try and find this angle A here. This angle A here. Now remember, the sine rule just simply says that the sine of the angle A divided by the length of the side opposite, in this case 15, is going to be equal to the sine of the angle B divided by the length of the opposite side to B, so that would be 13 in this case, and it's also actually equal to the sine of the angle C over the length of its opposite side, C, this side here. So we can use any pair of these two fractions here to work out any particular angle or side. So I'm going to try and find this angle here. So I'm going to get the sine of, I'm going to say the sine of A, in this case, divided by its opposite side, in this case, which is 15. That's going to be equal to, now I need to know an angle and its opposite side. So I only want one unknown in this particular equation, and I have my unknown here. So the other two here, I must know what they are. So I'm going to use this angle and this side here. So I'm going to use sine 60 divided by 13. Okay, so there are four things here. I have three of them, so I can work out the one unknown. So let's do that. Now we have a fraction equal to a fraction here, so normally what you can do here is multiply across by 15 times 13, or the quick way of doing it is just simply to cross multiply. So multiply the top by the bottom, and that will be equal to the bottom times the top here. So in other words, 13 times sine A will give me 15 times sine 60. Now I just want sine A here, so I'm going to get sine A equals 15 sine 60 degrees divided by 13. 13 here. Okay, so that gives me a sine of my angle A equal to 0.9993. 0.9993 to 4 decimal places. We'll just go to 4 decimal places here. Now, in order to find the angle A here, I have to do sine inverse. So I'm going to do I'm going to work out the angle A here. So the angle A then in this case is going to be sine inverse of 0.9993, and when I work that out I get 87.88 87.88 degrees. So my angle here at A will be 87.88. Now this is only one angle that can be a possibility for A, simply because sine is positive in the second quadrant. So there is a second angle that will have a sine of plus 0.9993. So what angle is that? Well, if I draw my x and y axis again here, so this is x, this is y, we've already worked out that the angle can be 87.88 degrees. That's going to be around here somewhere. Okay, so this angle here. So it can be an acute angle. However, 87.88, if that was, let's say, my reference angle, so let's say it looks like this. So let's say that's 87.88 degrees. The sine, and so my actual angle then that I'm looking at here is this angle here. This angle here is the second angle that will have a sine of 0.9993. So what angle is that? Well, it's just simply 180 degrees. 180 degrees minus 87.88. So if I work that out, I get 92.2. Let's say 92.2 degrees. Let's put another 2 there actually. 92 point, let's see, would that be right? 82.912. Okay, we'll just leave it at 92.2 for the moment. Okay, it's near enough anyway. So, in other words, this angle here, this angle greater than 90 degrees, or in the second quadrant, will be 92.2 degrees. So the sine of this particular angle here, 92.2 degrees, will give me 0.9993, and the sine of 87.88 degrees will also give me plus 0.9993. So I have two different angles here that will give me the same sine. So this is the ambiguous case that I was talking about initially. So there are two different triangles I can make where the angle A will be either 87.88 or 92.2 degrees. Okay, so that means I can have two different lengths here as well. I'll have two different angles here as well. So let's just have a look at those. Now, let's just move that up here. Okay, so my original triangle, I'll just draw it again here, will look like this. Lovely, just get rid of that a little bit here. Okay, so my original triangle looked like this. I had an A here, I had a B here, I had 60 degrees here, and C here. This was 13, this was 15 here. So I'm saying this particular angle here can either be 87.88 degrees or it can be 92.2 degrees. So you need to take both cases and have a look. So if this here was 87.88 degrees, what you have to do is take 180 degrees, subtract 87.88 degrees, and also subtract the 60 degrees, and that will give you 32.2 degrees. 32.2 degrees. So this will be my angle C if A is this here. Now if A is 92.2 degrees, then I do exactly the same thing again. I take 180 degrees, subtract 92.2 degrees, and also subtract the 60 degrees, and that will give me an angle of 27.8 degrees. 27.8 degrees. So that could also be C if A was this here. So you get two different answers for A. You can get two different answers for C as well. And you'll also actually find that when you use the sine rule again to find this side here, you'll get two different lengths for AB. So I won't go through that, it's just what I did up here. So it's AB could be, it's either going to be 7.99 centimeters or it could be 7.00 centimeters. So this is the ambiguous case here really. Because sine is positive in the second quadrant, you can get two different angles for A in this case. So that means you can get two different angles for C, and as a result you'll get two different lengths of this particular side here. Okay, now I just want to do one other example where you just have to be a little bit careful when talking about the ambiguous case and when looking at this second angle. In some cases it may not be possible to actually construct a triangle using the answer you got for the second angle. So let's have a look at where that might occur. So let's have a look at a second triangle. Now this triangle, again, let's see, we'll do ABC again. So draw it like this. Okay, so you've got, let's say, A here, you've got B here, and you've got C here. Now let's take 60 degrees again. We'll take 60 degrees here, and we'll take a length of 10 centimeters, and we'll take a length of 9 centimeters here. Okay, so let's work out, let's work out B. We'll work out this angle here. So again, we need these two here because we have those, and we'll take this one and B. So let's say sine of B, the sine of the angle B divided by its opposite side 9, that's going to be equal to the sine of 60 degrees divided by 10. Now let's just work that out, cross multiply again, so you get 10 sine B equals 9 sine 60. Okay, so that gives me sine B divided by 10 both sides, so that gives me 9 sine 60 divided by 10. So that gives me sine B equal to, when you work this thing here out, you get 0.7794. 0.7794. Okay, so the sine of what angle will give me this here? Well, there are two angles. There's one in the first quadrant, there's one in the second quadrant, because sine is positive in the second quadrant, and this is positive. So there are two angles that will give me a sine of plus 0.7794. What are they? Well, let's do it. The first one anyway is going to be, we just need to get the sine inverse of 0.7794. That will give me B, the angle B. So when I work that out, when I do that, you can do that on your calculator easily enough, you will get B being 51.21 degrees. 51.21 degrees. So that's an acute angle, that's fine, that should work, no problem. So B here will be 51.21 degrees. And from that then we can easily work out what C is. By just adding these, subtracting from 360, that will give me C. I won't do that for the moment. And now I want to look at the second angle that will have a sine of plus 0.7794. What would that be? Let's have a look. If we take again our x and y axis, okay, we have an x and y axis here. We have our angle here of 51.21 degrees, okay. Now we also know, because sine is positive in the second quadrant, we also know that if our reference angle here is 51.21 degrees, then this angle here will have the same sine. This angle here will have the same sine as 51.21 degrees. So what is that angle? What is this purple angle here? This obtuse angle. So let's have a look. How do you work that out? Well, it's just simply 100. It's just simply, let's see, let me get the color right here. Okay, it's 180 degrees minus 51.21 degrees. That will give me B, another angle for B, or another measurement for B, as 128.79. 128 degrees 0.79. So B can be this particular angle here, or this particular angle here. So we have two answers. Well, we know it can easily be this one here because it's an acute angle, and we have an acute angle here, 60 degrees. This is an acute angle here, so that's fine. What about 128 degrees here? Well, if you look at what you were given originally in the data here, you were given initially an angle of 60 degrees. We know that 60 degrees is an angle in our triangle. Now, if B was to be 128.79 degrees, that would mean if we take our 60 degrees, we take 60 degrees and we add 128.79. Remember, that's what we're saying our angle B could be, 128.79. If we add these two together, the angle that we know is part of our triangle and an angle that we think will be, if we add those together, we get 188.79, 188.79 degrees. Now, this is not possible. If we add two angles in a triangle and we get an answer that's greater than 180 degrees, that is just simply not possible, because the three angles in a triangle add up to 180, so it's not possible for two of the angles to add up to 180 or more. So we can reject this particular answer here. It's not possible to create a triangle in this case with an angle of 60 degrees and 128.79 degrees. So we accept this particular answer here. This is the only one we accept for B. From that then you can work out what C is, and from that then you can work out AB as well by just simply using the sine rule again. Okay, and that's it for the sine rule and the ambiguous case.